Let us now try to understand the behavior of the magnetic dipole in an external uniform magnetic field. Suppose the current carrying coil or the magnetic dipole is placed in an external uniform magnetic field of strength B arrow, then just like the electric dipole, the magnetic dipole would also have magnetic potential energy. It will also experience a torque. Let us see. The magnetic potential energy possessed by the dipole within the external magnetic field of strength B arrow is minus M arrow dot B arrow. Remember, minus P arrow dot E arrow for the electric dipole. That is minus MB cos theta. Theta is the angle between the two vectors, that is M arrow and B arrow. U naught for theta equal to 0 degree state, the least magnetic potential energy state. The least magnetic potential energy state, theta 0 degree, cos theta 1, so minus MB. This is the most stable state. Call it as the equilibrium state. Well, if the dipole is disturbed and, well, it is taken to an excited state, that is the theta state, same as this, then the magnetic potential energy would be minus MB cos theta, that is an excited state, more magnetic potential energy. And in that state, just like we learned in our study of the electric dipole, the dipole would experience a torque. There it was P arrow cross E arrow. Here it is M arrow cross B arrow. So easy, so simple. Just you have to do a parallel study. So tau is MB sin theta. And what is the role of this tau? The tau will try to bring the dipole. Now I am thinking of the dipole just like a bar magnet, So if it has come like this, it will like to come to the theta equal to 0 state. But then due to inertia, it will overshoot. Then this, and like this, it will execute oscillation. Let us investigate if this oscillation is an SHM. Let's see. It will be SHM only if theta is very small. If theta is very small, then sin theta equal to theta in radians, and then the restoring torque would be MB theta. M is constant, B is constant, so it's a constant multiplied by theta. Theta is the angular displacement. I call K slash, capital K slash, as the Hooke's constant here. Value is M into B, and if that is so, then the restoring torque is proportional to theta. It is a case of angular SHM. If it is a case of angular SHM, then it has angular frequency omega, the Hooke's constant divided by I dash. I am using I dash for the moment of inertia of the dipole, because I have been using for the current. So I dash is the moment of inertia of the dipole. So moment of inertia about this axis, because the dipole is rotating like this. Time period. So time period will be 2 pi by omega. So it is 2 pi I dash upon K slash, and K slash is MB. So I get the expression for angular frequency and time period. Now here I like to remind you something. We have this current carrying coil as a magnetic dipole. It is placed in an external magnetic field of strength B. It experiences a torque. When it experiences a torque, it will have angular acceleration. Angular acceleration will increase its angular velocity. The coil will rotate in the magnetic field. It is the case of an electric motor. So with this concept, with this idea, we can learn the working principle of electric motor. Electric motor and moving coil galvanometer, something similar, both very important for your syllabus. But both these devices, the electric motor as well as the moving coil galvanometer, I will not discuss in this particular video. I'll have a separate video for that. I'll build up a separate video, and post it on YouTube. Only thing is that in the case of moving coil galvanometer, the restoring torque is going to be opposed. This restoring torque, or I can call this time now as a deflecting torque, because if it is a deflected the coil in the field, then I can have the coil suspended from a suspension fiber, and there will be a twist in the fiber, and there will be a restoring couple set up and all that principle that we will discuss in a complete video on the working principle of a moving coil galvanometer. So with this, you understand the different properties of the dipole, the field, the potential, and also the behavior of the dipole in a uniform magnetic field. Now, what if the field is not uniform? Then surely, apart from the torque, it will also have force, because on one of the pole where the field is strong, there would be a greater magnetic force, because the magnetic force once again would be Q times B. But mind you, Q here is the magnetic charge, unit ampere meter, pole strength. So in that case, the dipole while rotating will also translate. So all these ideas are going to help you a lot in understanding the behavior of the materials with the magnetic properties when they are placed in magnetic field, uniform or non-uniform.
If you love the video and want me to make more useful videos for you, subscribe my channel and hit the bell icon to stay updated.